once it starts. All right. So we took a little bit more time than we needed, but I really wanted you to practice this, especially if you haven't been practicing on the homework. This is a good time to practice. And then if you feel like you're uncomfortable with it, we just practice some more. And if you don't get it, stop by my office hours and we can practice your homework problems together. Right? And if you're watching this recording, hopefully you guys gave yourself some time to do these problems first before you start watching this. Okay? So try these out and see what you guys get. The notation for something like this on number 1 is a little strange if you've never seen it before, right? There are essentially, I'd say, like 3 functions there, but it's not 3 composite functions. It's not an inner, then a middle, then an outer, right? It's one function multiplying with another function. So an easy way to see that is you can see it as x multiplying with cosine of x squared, right? Now, you don't need to rewrite it like this. I just like rewriting it just to show you guys, right? So you're going to be applying the product rule here, right? You're going to be applying the product rule with this as my first function and this as my second function. But my second function is actually a composite function, right? Cosine of x squared has an inner function of x squared, and it has an outer function of cosine of some stuff. Well, what's that stuff? Well, it's that x squared right there. So when I do the derivative of that second function, I have to apply the chain rule. And if you don't remember the chain rule, let me write that off to the top right here. If you have a function g of x inside a function f of x, and I take the derivative of that, right? And I take the derivative of that, that's going to equal to the derivative of f, but evaluated at the same stuff that it was in the beginning. So whatever that function is inside there, multiplied with the derivative of the inside function, right? Multiplied with the derivative of the inside function. So whatever g of x is, you take the derivative of that and multiply it with the derivative of f of x, evaluated at what g of x is. You're like, what? And you'll see it when we come into play here. So let's go ahead and apply this product rule right here. So y prime is going to equal to the derivative of the first. So derivative of x is just 1 times the second function, right? Cosine of x squared. So nothing's changed so far with this product rule, right? Derivative of the first times the second, plus, now here is where it gets tricky. The derivative of the second, right, is where we do the chain rule here. So derivative of the inside function, right? If I take this and I'm going to run out of space here. If I take the derivative of x squared, right, dx, x squared is going to be 2x, right? So that's going to be 2x right here, times the derivative of the outside function. Derivative of cosine is negative sine of some stuff. But again, what's that stuff? I'm going to write it out right here as negative sine of that stuff, and that stuff is going to be the x squared that you started with, right? The x squared that you started with. And that's the derivative of the second function. It's the derivative of the inside times the derivative of the outside, okay? And this is, of course, still being applied with the product rule, which is multiplied with the first function, and the first function is just x. And that's it, right? If I don't ask you to simplify, you just stop there, right? If you don't need to simplify, you stop there. And just like on a test problem, I actually prefer it if you stopped here. It just makes it easier to grade. But if you really want to simplify, because I might have given you like a multiple choice problem, then, you know, distribute the 1 here. This is going to be cosine of x squared plus 2x. That's not a plus. There's a minus there. So I distribute the minus with that plus. It becomes minus 2x squared sine x squared, right? Parentheses helps with notation for some people to see. And, you know, you can rewrite it with that and use parentheses if you want. But at the beginning here, right, you got to get yourself comfortable with reading these functions, right? X times cosine of x is 2 functions. X is a function itself. Cosine is the other function, right? So we apply the product rule. But when you look at the product rule just for the second function of cosine, cosine has a composite function in there. And this is the part that's tricky. Does the square apply to the entire cosine, or does it only apply to x? And just speaking from notation-wise, just for practice sake, if you see something that looks like, this is a side note. This has nothing to do with this problem here. Side note, sadly not written on the side. If I have cosine of x squared, this traditionally means it's cosine of x squared. You see that? Whereas if I had cosine of x quantity squared, that's the same thing as cosine squared of x. right? So get the hang of that. Get used to seeing this. Trig functions and log functions and all those other functions, they have the weird notation, but it's picked up that way, and it's something you got to get used to seeing. Okay, so that's the idea behind that, and you can see that how that splits out. All right, hopefully you're okay with that. You guys have any questions on number 1? We'll pause it for a second. How do you feel? Any questions on it? Are you okay? I'll double check again when, once we finish up number 2. I want to see how you guys are feeling about this, because chain rule is a big rule, and it is something that you need to apply repeatedly. So I'm going to move over here. Let's take a look at number 2. Let me know, by the way, if you need me to go back anywhere, or if you are writing the notes and you need me to slow down to explain some stuff. All right. This one right here, right? You can clearly see that it's a quotient, right? You have a function divided by another function, right? You have a high function. Your high function is x, and you have a low function, which is tangent of 2x. But I hope you guys see tangent of 2x is a composite function, right? Tangent of 2x, right, has a inner function on the low. It has an inner function of 2x, and it has an outer function of tangent of some stuff. And that stuff in this case is 2x, right? So if I'm trying to do the quotient rule here, right, low is tangent of 2x. D high, the derivative of x, is just 1, right? Minus high d low. Now the d low parts require the derivative of the inside, which is 2. Let's write that out. Taking the derivative of the inside and the derivative of the outside. Derivative of tangent x. Have you guys memorized that yet? Derivative of tangent x is secant squared x, but it's not going to be of x this time. It's going to be of 2x, because that's what gets plugged into here. So derivative of the low is this guy right here. Let's get the inner first. Derivative of the inside, which is 2, times the derivative of the outside, which is secant squared 2x. Right? And this is all, of course, being divided by tangent of 2x quantity squared. And again, I would leave it there, right? I would leave it there. I wouldn't go any further. I mean, you could if you want. Secant and tangent of 2x, they'd all definitely cancel somehow. But I'm just letting you know, if you do that without showing the work of how you simplify it, I'm going to be very suspicious if you do that on the test. Because, like I said, a lot of people have been using photomath, and it's fairly easy to tell when you guys use photomath. Like, you guys don't even understand how ridiculous how'd the 2 get there? Oh, Max, are you talking about this 2 right here? In the part that I highlighted? So the derivative of tangent of 2x, you require the chain rule. And the inside function is this 2x right here. And the derivative of 2x is this 2, right? That's where that 2 is coming from. It's the derivative of 2x. Yeah, that's how that works. But yeah, as I was saying, so hopefully that answered your question, Max. But as I was saying, there's another app too. I forgot. I know what. I haven't tested it out yet, but it did the same thing when I had someone else who was showing it to me. Of the way it simplifies is just weird, right? Like it's not wrong. It just does some weird stuff. And for this one right here, for example, right, the furthest simplification without raising any questions, if you just rewrite it for me, right? If you just rewrite it for me, that's awesome. And I take your answer, right? You just rewrite it, and some people might not like the squared outside, they like the squared inside, and that's perfectly fine. You could do it like that too. That's perfectly fine. But if you go further and you try to start canceling things out to make it simple, it just gets weird. Like, I don't know how to explain it. Let me see here. If you want to split it up, and this is what I saw on like that program, right? I saw some of them split it up and rewrite the tangent 2x over here over tangent squared of 2x minus 2x secant squared 2x over tangent squared 2x, right? So the tangent 2x and the tangent squared 2x would cancel out one of the tangents, and this would be rewritten as 1 over tangent of 2x, which would then get rewritten as cotangent of 2x, which you say, no, that looks so much cleaner. And I agree, it does, but it's just unnecessary, right? And the same thing can be said about the this guy right here. the 2x secant squared tangent squared. Secant is the same thing as 1 over cosine. Tangent is the same thing as sine over cosine. And again, it's just a weird thing to see. Some people will write it out as like that turns into cosine. I'm not even gonna write this out. It just looks weird. It turns into cosine to the 4th over sine squared, and it's just unnecessary. You know what I'm saying? You know what I'm saying? Like all this simplification stuff, it just gets awkward and weird, and then it's easy to tell that you shouldn't have been doing that. So you could stop here. You don't have to go any further. And if you really wanted to, I really suggest you just leave it here. It just makes your life easier, right? The calculus part is just me knowing that you know that it's low d high minus high d low over low low, and that you're able to identify the chain rule. If you can do those for me, you're good. You're golden. You're set. You don't have to worry about anything else. Okay? Anyways, long-winded talk about that, but I need to know, how are you guys feeling about this? I'm going to go ahead and change the slide. Let me know. Just give me a thumbs up or a thumbs down. How do you feel about this right now? Okay, just a quick check. How do you feel? If you guys could on the pair deck, let me know. And while you're doing that, I'm going to move us on to the next set of problems, which is going to be how to calculate the derivative on a table, right? How to calculate the derivative on a table. So let's take a look here. Let's say I have something like this. Go ahead and paste it onto here. Boom. And remember, we learned how to take derivatives from tables, right? It's not that bad. Yeah. Just a quick refresher. You don't have to do this on there, but just a quick refresher, like how to use a table to find derivatives. I might ask for things like, let's say I have, for example, a function v of x is equal to f of x divided by g of x, right? And I wanted you to find v prime evaluated at, I don't know, let's say 2. Right? No, let's get one that doesn't have fractions. V prime of 1, right? And we know that that's going to be equal to the quotient rule applied here, right? Which would be low d high minus high d low. Get the x out of there, knock me. Right? All over low low. Right? But we would be evaluating this at the 1 that they're telling us to look at. So it'd be g of 1 times f prime of 1 minus f of 1 times g prime of 1 all over g of 1 squared. Right? And then you just look at the table. Right? When we do these problems, we would look at the table and see, oh, g of 1 is equal to 1. Right? The 1 part right here, it's all these values. So g of 1 would be equal to 1 times f prime of 1, which is negative 1, minus f of 1, which is 5, times g prime of 1, which is 2, all over 1 squared. You guys remember how we did this, right? Does this look familiar? Right? You had 4 test problems on this, by the way. So if you were struggling on the test, right, this is how you're supposed to do those problems. You're supposed to apply the rules based off of what the function definition is, and then you take the derivative of it using those rules and then plugging in the values into the table. So what I want to do for this one now is apply the same rule, but now using the chain rule onto here, right? Now using the chain rule. So let's go ahead and take a look at this one. And let's say for part A, right? For part A, I'm going to define the function h of x to be equal to f of g of x. F of g of x. And for part B, I'm going to define this as h. Now let's go with j. J of x. Why not? That's the letter I never really use. But j of x is going to be g of f of x. So you see the difference here is now we're dealing with these composite functions. You guys see that? My inner function is g of x and my outer function is f of x, right? And for B, it's switched around. My inner function is f of x, my outer function is g of x. So here's what I want you guys to do for me. I want you guys to attempt this problem, and I want you to find, right, for this one, I want you to find h prime of 2 for me. I want you to find the derivative of this one evaluated at 2. And I'm going to put that up right now onto the slides, onto the pair deck, right? For part B, I want you to find j prime, so the derivative of the j function, but this one I want you to find it evaluated at 1. Evaluated at 1. So if you don't know where to start with this, right, understand that you're applying your different derivative rules. But this one in particular, I hope you guys see both of them for A and B is just the chain rule, right? And if you don't remember the chain rule, let me write that out for you, right? If I'm taking the derivative of a composite function, f of x, f of g of x, right? That's just equal to the derivative of the inside, so it's the derivative of g of x, multiplied with the derivative of the outside, so it'll be f prime, but it's not f prime of x, it's f prime of what's inside of it, which is g of x. See that? So that's the rule I want you to apply for this one. You're not applying the quotient rule, you're not applying the product rule right now, you're applying the chain rule. Can you guys apply the chain rule for these two problems and see if you can hash this one out? So I have them defined. H of x is right here, f of g of x, and j of x is right here, g of f of x. So if you guys could try that out. I'm going to go ahead and let you guys see where you guys are at for these two problems. Let's go for about 5 minutes. Yeah, let's go for about 5 minutes and see how you feel using a table to help you find your derivative of a chain rule. So go ahead and try that out. It's on the Pear Deck. The Pear Deck is open. Go ahead and give that a shot. Let's go with 5 minutes. I'm going to go ahead and start that timer right now. There we go. Boom. And I'll put the timer. That's too big. Let's go over here and put that like right there. Beautiful. All right. Man, this whole distance learning thing, you guys keep working. I'm just rambling myself, but I was looking at the pacing of where I was last year for teaching these topics, right? And I kept joking with the students, but I was a little bit serious with them. I was just saying, like, man, we're so far behind. Pacing wise, we're so far behind. We need to actually catch up because we're so far behind. I should be on this chapter already by then, right? And I looked at the date that I was saying that and doing that last year. This topic that we're learning right now of the chain rule, I taught it last year, apparently, second week of October. And right now we're in the first week of November. So we're 3 weeks behind the usual schedule from before. Last year I taught it like right around here on around October 12th. And this year I'm teaching it around here starting November 3rd. So I'm like about 3 weeks behind. 2.5 weeks behind. And I'm like, well, crud. That sucks. So we got to find a way to rush through it. And that's something that's on me. I got to figure out a way to, I don't want to rush through it though. I want to make sure you get it though, you know? So I can't just like, here's some stuff. Go do this. So I don't know what we got to do. We got to do something. And I've been like trying to wrap my head around it. What can I do to try to get this going? And I don't know. Some of the other teachers are saying like some students requested that they do flip learning, where the teacher records like the lecture of how to do it. The kids watch it for homework, and then in class you do practice problems. And I don't know how I feel about that because you're already watching these videos of me live. I don't know if that would be, worth it. to watch a pre-recorded lecture, and then we do practice problems in here. Kimberly's saying yes. You think that's better? You think you like that more? Brian? No, Monica? Yeah. I don't know either. Like, I was like, I wouldn't. Yeah. I like this recording the lecture live, so then if you don't get it, you can go back and watch it, because it's the same thing. I'm doing the same stuff I would do if I was teaching it live, right? It's the same stuff if I would record the same things there. But I'm like, would that give us more time? Kind of defeats the purpose of yeah, that's the other thing. Like, it wouldn't be, but you still get the live part, Brian, where we would do these problems together. But then that, I think about it, the more I think about it, then that's the same thing as you come into office hours. If you have questions, you can just come to office hours. This is like forced office hours if I think about it that way. Scratch that. Never mind. Forget that. No, I don't want to do that. I do like it when you guys show up to office hours, though. It's fun. We get to do problems where I'm not just like lecturing nonstop like this. But maybe, I don't know. I don't know what to do. We'll figure something out. I don't know. I'm feeling a little burnt out. All right. Got about 10 seconds left. Let me take a look through here. How'd you guys do? You're almost there. Looking pretty good. Some of you guys just have the answers, and I'm going to be honest with you, I don't know the answers yet. I need the work, and it makes it easier for me to grade. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of you wrote down something. I appreciate the 11 of you that wrote down something. Let's take a look here, right? So if I'm asked to take the derivative of this function h of x, and h of x is defined as f of g of x, right? I want to find the derivative first before I find the derivative and evaluate it at 2. So I'm going to move this down a little bit. So h prime of x is going to equal to, and here, you just apply the chain rule. The chain rule. What's the chain rule? It's the derivative of the inside. Well, what's the inside function? The inside function is g of x. So what's the derivative of that? Well, that's just going to be g prime of x, right? When you're looking at just function notation, you're trying to see what's the derivative of g of x. This is g prime of x. If we don't actually have it, I don't know what g prime of x is, but I do know that I can represent it with g prime of x, right? And then multiply that with the derivative of the outside function. What's the derivative of the outside function? F. Well, that's just going to be f prime of some stuff. What's the stuff that goes in there? G of x. That's it. Now, they want us to evaluate this at 2, and this is where the fun goes in, right? Fun. G prime of x is going to become g prime of 2, and this is going to multiply with f prime of g of 2. Now be careful with this here, and let's take a look here. G prime of 2 is 3/2, right? That's what that is, 3/2. Times, I don't know what f of g is, but I do know what g of 2 is. Do you guys see that? G of 2 is equal to 3. So what I can do is replace that with f prime of 3. And this is what, by the way, what h prime of 2 is equal to. Apparently, h prime of 2 is equal to 3/2 times f prime of 3. Well, do I know what f prime of 3 is? Do I know what f prime of 3 is? I do. I go back to my table and I look at it. F prime is this one right here. Of 3, it's this value right here. Do you see that? It got modified, right? I don't look at it on the same row anymore, but it's there. And f prime of 3 is -1. So when I write this out, h prime of 2 is equal to 3/2 times -1, right? Times -1. So my answer for this is just going to equal to -3/2. -3/2. Trippy stuff, yeah? It's kind of fun, though, right? Kind of fun. And I know you're like, Nachman, your definition of fun is weird. And I agree. But it is. It is kind of fun. And if you're judging me on that, shame on you, right? Don't judge me for my weird taste. All right, anyways, let's go ahead. Let's do the next one. It's the same concept, right? Think of that right there. Makes sense now? Yeah, good, good. That's really cool. And it's the same thing, right? For this one, you just have to identify what's the inside function, right? And the inside function in this one is f of x, right? So I'm going to go ahead and move this one down just a little bit. Hesitating here. I'm going to move that one down just a little bit. And I'm looking for the derivative of j of x, right? So same thing. Derivative of the inside function now is f prime of x, right? And you multiply that with the derivative of the outside, and this one switched around, so this one's going to be g prime of f of x. Which again, we go ahead and evaluate this at 1. This will be f prime evaluated at 1 times g prime evaluated at whatever the heck f of 1 is. That's all that is. Evaluated at whatever the heck f of 1 is. So let's see here. We're going to go ahead. F prime of 1 is, let's see here. Let's go with a new color because it's starting to overlap. F prime of 1 is this one right here, -1. Boom. Done. Multiply that with g prime of, well, what the heck is f of 1? F of 1 is just equal to 5. So I'm looking for g prime of 5. Right there. What the heck is g prime of 5? What the heck is g prime of 5? G prime of 5 is -1/2, and that's what I'm going to replace this guy with. -1/2, and that's going to be multiplying with -1. So you guys should have got, right, j prime of 1 should equal to +1/2, and that's it. And that's it. I got distracted by a drawing. David, what is that? A penguin? Birdie? Okay. Oh, I see it. That's the beak. Anyways, yeah, it just comes out as 1/2, right? So hopefully you guys are able to get that. Hopefully you guys are okay with seeing how the chain rule works. Does that make a little bit more sense? Like when you're dealing with the chain rule, it's just the derivative of the outside function using whatever rules you need to, and then multiplying that with the derivative of the inside function. And again, using whatever rules you need to, product rule, chain rule, addition, subtraction rule, all those rules apply and they just start stacking on top of each other, right? They just start stacking on top of each other. That's all that is. So that's that one right there. And I'm going to go ahead and move on because there's like some other like side topics we got to cover real quick. And yeah, I'm going to do that real quick right now. So let's scroll this down, and this is going to be like the last part of this section, this small section, and I want to try to start on the next section after. So if you want to title your notes, right, this is a little bit of a continuation of the chain rule, and it's applied to these guys called the parametric equations. So I'm going to write that out. Parametric equations. Equations and derivatives. All right, there you go. Parametric equations and derivatives. That's going to be the topic for this one right here. So if you guys want to write that down. A parametric equation is something I'm pretty sure not a lot of you have seen. A parametric equation is an equation, it's actually a couple equations, and your x and y values are dependent on a third variable, and the third variable is usually a t for time. So at a specific time, you can find out the x value and the y value of something, but they're separate equations. And let me show you what I mean. A parametric equation looks something like this. And this is like, again, this is a side note. I just want to show you something, but it is something that is covered on the AP exam, so you need to know a little bit of it just in case they give you something like this. So normally, right, a regular equation would look something along the lines of like y is equal to 2x plus 5, and whatever x is, it affects your y value. Yeah? Those are just regular equations. Parametric equations, actually, sorry, I shouldn't say regular equations. Those are Cartesian equations. I should know the name of that. I'll come back to you on what the name of our regular equations are for. Stop saying regular, Doc. It's just regular. Anyways, for a parametric equation, what makes it different is your x is a a function of another variable, usually t, so it'll be something along the lines of x is equal to 3t minus 2, and y is equal to t squared minus 4. And that's the idea of a parametric equation. And traditionally, when you do a parametric equation, you have it set, you have your dependent variable, your independent variable, in this case t, defined on a specific interval, right? Traditionally, it'll be something along the lines of like, let's look at t from -3 all the way up to 2, right? So you still get x and y values. You still graph this on the Cartesian plane, but you move it based off of what t is equal to. So when you make your tables before, right, you would make your x, y tables before. You remember that? And you'd plug in like numbers for x and you get a number out for y. That doesn't work in this case, right? You plug a number for x, you don't really get a number out for y easily. You can get it, but it won't be easy. It actually would be easier for these parametric equations to just throw in a third table, right, a third column, and call that for t. And you plug in numbers for t, like plug in -3, -2, -1, 0, 1, and 2. And I wouldn't plug anything else. I mean, you could plug numbers between them, but I would stop there because my domain for my t goes from -3 to 2, right? And then how does that work? Well, you take your t and you plug it into these parametric equations, so you can see where the point is. So when you start off this thing at t is equal to -3, you get -3 times -3, which is, I'm sorry, -3 times 3, which is -9, minus 2, I get -11 for my x value. And if I plug it into my y equation, -3 squared is 9, 9 minus 4 is 5. So if I was graphing this thing, right, right, my starting point would be at like -11, 5, -11, 5, and I go and plug in my next value of -2 and see where that goes. So -2 times 3 is -6, minus 2 is going to give me -8. -2 squared is 4. 4 minus 4 is 0. So the next point is going to be at -8, 0, which would be like right here. And the way this would work for a parametric equation is you would connect it from here to here. And you're like, I mean, that just looks like a line. It kind of does, but you actually have to show that it's going in this direction. So you draw a little arrow there to show that it's going in that point right there. And it actually might curve, because there's probably some more values in between that for t, which from -3 to 2, that it actually makes a curve. And I don't know how it curves right now, but I don't want to plug it all in. But that's the idea. And then, you know, you plug in the next one and you say, oh, -1 times 3 is -3, minus 2 is -5. -1 squared is 1, minus 4 is going to give me -3. So the next one would be -5, -3, which would be like somewhere over here. And again, you draw that, and then you draw a little arrow there, and that would mark it for you, right? But don't copy it on the graph. Or actually, if you already copied it on the graph, just leave it there. That's not that important. It's just an idea of another way of graphing your functions. And the cool way about graphing parametric equations is they're no longer like regular equations that we graph where they have to like pass the vertical line test. These parametric equations could actually come out and start looping around like this, and you just have the arrow to tell you that, oh, it travels this way. And it's kind of neat to see, right? And I don't know if you guys have seen some of those pictures before online. Like people will draw out symbols like the Batman symbol, or draw out like really crazy things, and they're using parametric equations to do that because it allows them to loop back around and whatnot. I don't know if you've seen it. I'll find a picture of it. I'll show you guys next time. It's kind of cool. Anyways, long-winded side story about parametric equations. But what I wanted to show you is, how does this connect to calculus, right? Well, we need to find derivatives of things, right, in calculus. So if I had, for example, I was looking for the derivative of y, right? We write that as y prime. But you guys remember, right? Y prime is just a shorthand notation for the change in y over the change in x, which is that dy dx deal. Well, the y function is not a function of x in this case. The y function is a function of t. So technically, right? Technically, if I'm looking for the derivative here, let's write this in blue. If I'm looking for the derivative here, right? I don't actually take the derivative of that with respect to x. I hope you guys can see that. If y is equal to t squared minus 4, if I take the derivative of this guy, it's going to be with respect to t, right? So this is actually going to be dy dt instead of dy dx, is which I normally want, right? I normally want dy dx, but I'll get dy dt instead. And that's because of the t squared in that 4 there. And the dy dt comes out to be, hopefully you guys agree, it's about 2t, right? 2t, yeah? I can do the same thing for this equation right here. X is equal to 3t minus 2. I can take the derivative of this guy with respect to t as well. And I end up with dx dt, right, is equal to 3. You guys okay? I know it's weird, but hopefully you're okay with this, right? I'm taking the derivative of these two equations, these two parametric equations, with respect to the variable that's there, right? Traditionally, we would always do that, but it was always, like y is equal to like x squared, and you would just get your dy dx from here, right? But that's not the case here. Your x and your y's are actually in terms of t's. So my derivatives there would be in derivatives with respect to t's. Now, my ultimate goal is to find dy dx. We always, when you take the derivative, you're looking at the change in the y over the change in the x. And if I start to try to look at that with the change in the t, you end up with like three-dimensional calculus. And we do that, but not in our class. If you continue with calc, calculus goes up to 4 different levels. There's Calc 1, which is what you guys are taking, AB. There's Calc 2, which is BC. It's basically AB with a little bit more topics, but in the university level, Calc 2, you just continue and you just move on. You don't have to relearn everything in Calc A. You just apply it. And then there's Calc 3, which is what I'm trying to talk about right here, which is three-dimensional calculus. So you have a third variable in there. And we're not quite there yet. I don't want to trip you up with that. So I'm just going to go with this right here. If I'm looking for dy dx, I hope you guys can see that if I just take dy dt and divide it by dx dt, right? If I divide that ratio with the ratio of dx dt, right, you end up with this. You end up with dy dt times, right? You keep the top one, you flip the bottom one to dt over dx, and then you change it from division to multiplication. And look at what happens here. Your dt's will cancel out, and you end up with what we're looking for, which is dy dx, right? You end up with dy dx, which means if I just divide my dy dt by my dx dt, I end up with my dy dx, which is what I was looking for. So this is equal to, you ready for this? 2t divided by 3. And that's your dy dx for these parametric equations, right? That's your answer for this one. I know I went on a long-winded talk, but basically if you didn't catch any of that stuff and you're just like, what the heck is this guy talking about? Just take the derivative of your x equation and the derivative of your y equation and divide the dy with the dx, and you get your answer for the derivatives of these parametric equations. So you're going to come across problems that look complicated. I promise you, you're going to come across, and they're going to look complicated, especially when you're like, oh crap, there's a x equal to something with a t and the y equal to something with a t. And I'm just trying to let you know, don't panic. Take the derivative like you normally have, and then just remember this. If you take dy dt and divide it by dx dt, you end up with dy dx because the dt's cancel out. And this will work for any letter, by the way. It doesn't have to be dt. It could be like dj or ds, d, whatever, right? It could be d of anything, d thetas even if you're dealing with angles, or drs if you're dealing with radii. All of that, it will work the same way. Just pay attention to it. You can treat these guys like the variables that you've done with in the past, okay? So that's that one. I don't really have much time to do some practice problems with that, so hopefully you guys are okay with that, right? Hopefully you guys are okay with that. I'm going to go ahead and move us on to the next section. For homework, I hope you guys have been doing the practice problems that I have posted. I'm going to have some more practice problems for you guys to do for these chain rule problems, okay? So keep that in mind. Well, it's just basically practice, 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 okay? All right. Anyways, with that being said, let's go ahead and move on to the next section. That's the end of that section for the chain rule. And don't forget it, though. It's going to apply to this part as well. The chain rule, you have to learn that first before you learn this one right here, which is implicit, that's not how you spell implicit, derivatives, differentiation, implicit differentiation. Okay, let's take a look at that right here. What the heck does that mean? What is implicit differentiation? Well, in order to learn what is implicit differentiation, you're going to have to learn this first word, which is explicit differentiation, right? Explicit differentiation sounds like a lot, but it's actually not too bad, okay? Explicit differentiation is what we've been doing, right? Explicit differentiation is what we've been doing. So let me show you what I mean. So something that's written explicitly is something like y is equal to x squared plus 1, or heck, even f of x, right, is equal to like something along the lines of like the square root of 4x cubed plus 2x minus 1, right? That's explicit. And what it means for it to be explicit is basically your function is defined explicitly with one particular variable. And usually it's x, right? If you're dealing with time, then it's usually time. It's just one variable there, and it's your dependent variable is equal to only your independent variable. And your independent variable could be multiple times, like x cubed plus 2x. It's still explicit because once you find out what x is, you plug it into both of them, right? It's the same value that goes into both. Whereas implicit, it's not like that, sadly. For implicit, did I spell implicit correctly? Do you ever look at a word so many times it looks like it's spelled wrong? That's what I'm looking at implicit right now. It doesn't look like it's spelled right, but I think that's right. For implicit differentiation, equations, right? Those equations look something like this, where it's a mixture of your dependent and independent variables together. So you might have something where it's like x squared minus 2y cubed plus 4y is equal to 2. And that is your implicit equation. That is your implicit equation. Another one might be something along the lines of this. Like you'll get something like x times y minus 2x squared plus y cubed is equal to x plus y. So when you have something implicit, you just can't get the y by itself pretty much, right? You can't solve it for y. Whereas other times you can make it explicit. You can solve for y. Like, for example, the easiest one is writing something into slope-intercept form, right? When you get the y by itself, you get a line, and you can have that explicitly as y is equal to something times x, right? For implicit forms, it's a little bit more difficult. Like, you could do it. It just takes a little bit more work. That first one I have right there of 2y cubed plus 4y, I wouldn't even bother. I don't know how to get that into an explicit form. So I would actually just deal with it implicitly. And I'm going to show you that today. How do I get the derivatives of things that look like this? Right? How do I get the derivative of things that look like this? And what I'm going to show you is we're going to be applying the chain rule here. I know you're like, we just learned the chain rule, but it's going to be applied here. Okay? So let's take a look here at some examples here. Right? And before I do that, basically it's the idea of this. We're going to differentiate. And I'm going to use this new this term right here. And you guys have not been hearing me say it. With respect to x. With respect. And that's the big thing here. What are you taking the derivative with respect to? Right? Traditionally it's with x. But you'll see what I mean here. So for example, right? For example, if I was asked to take the derivative of x cubed with respect to x, that means I'm looking at this thing with a dx here. Now here's the thing. Using the power rule, you already know that x cubed comes out to be as 3x squared, right? You guys agree? X cubed, the derivative of that is 3x squared using the power rule, right? But what you might not know is that there is a chain rule going on here, and we just never show it. right? We just never show it. And the chain rule is this. The x cubed is your outer function, and the inner function is x itself. So this right here, this is actually the derivative of the outer function. 3x squared is the derivative of the outer function. You're supposed to multiply this with the derivative of the inside function. And here's the thing. Do you know what the derivative of the inside function is? Well, d dx of x is simply equal to dx over dx. So technically, right, when you were taking the derivative of x cubed, it's technically 3x squared times dx over dx. You know why we don't write the dx over dx? You know why we don't write that? Because dx over dx is exactly like the same rules for any fractions that you have, right? It's the same variable on the top with the same variable on the bottom. So dx dx actually simplifies out to just 1, right? It just simplifies out to 1. And that's why we don't write it. But it's technically there. Using the chain rule, it's technically there. Now, what if that wasn't an x then? What if it was something along the lines of like a y? So if I was taking the derivative with respect to x of y cubed, right? If I was taking the derivative of y cubed with respect to x, what would that look like? Well, it's the same concept, right? You have an outside function of something cubed, and you have an inside function of y. So the derivative of the outside would be 3y squared. So far, so good. But this needs to multiply with the derivative of the inside function. And the derivative of the inside function with respect to x is not going to cancel out this time. When you do that and apply it to here, it's going to come out to be as dy dx. So this is the derivative of the outside function, and this is the derivative of the inside function. So when you take the derivative of something with respect to a specific variable, you have to make sure that you're giving it that respect and that answer to follow up with. We just kind of canceled it out when we did it explicitly, because when you do it explicitly, you're always doing it with respect to the variable that's there anyways, right? So if I took the derivative of f of x here with respect to x, I didn't have to worry about it because it would always work out as dx over dx, and they just cancel each other out. But if you include a different variable and you're taking the derivative with respect to a different variable, you got to make sure you chain rule that and take the derivative of that inside function. Okay? Let me show you another one. A couple of them. So let me show you a couple of them. Let's take a look here. Let's say I was looking at this problem right here, and I was asked to take the derivative with respect to x of x plus y. Of x plus y, right? The derivative, well, why did my voice crack right there? The derivative of x, you would agree, is 1, right? Because the derivative of x is of something to the first power is just 1x, right? To the 0 power, which is just 1, times the derivative of the inside function, which is dx over dx. But again, dx over dx just cancels, and you're left with just 1. Plus, the derivative of y is just going to be 1 as well, because it's 1y to the 0, right? The derivative of the outside function. But that's going to multiply with the derivative of the inside, which is going to be dy dx. So what's the derivative of this thing as a whole? It's going to equal to 1 plus dy dx. And that's your answer. Derivative of x with respect to x is just equal to 1. The derivative of y with respect to x is going to equal to dy dx. Right? dy dx. Trippy stuff. I hope you're okay with it. Let's do one more. All the rules that we've learned, product rule, quotient rule, all that still applies, right, to these chain rule problems that we're learning here. So if I have, for example, right, I'm taking the derivative with respect to x of x y squared. Xy squared. So can you guys take a look at that one right here? This is two functions. I know that you're like, no, just two variables. Yeah, those two variables represent two functions, and one of them is multiplying with the other one. So if I was to take the derivative of this, I need to apply the product rule, where x is my first function and y squared is my second function. You ready? The derivative of this would be the derivative of the first, which is 1, multiplied with the second function, which is y squared, plus the derivative of the second function. Now, this is the part that's tricky. The derivative of the second function is 2y right? Right? Derivative of y squared comes out to 2y. You bring down the power rule, and I get 2 minus 1, which is 1. So I get 2y. But this is the part that you got to remember. It's not just 2y by itself. It's 2y times dy dx. You got to show that chain rule of when you take the derivative of a function or a letter that doesn't have the same matchup here. And we actually did that with, you actually do that with the first one. I should have shown that here. The derivative of x is not technically just 1. It's 1 times dx over dx. And again, it all comes down to you paying attention to what you're taking the derivative with respect to. And I'm taking the derivative with respect to x in these problems. So that's why that dx is there. I'm taking the derivative of x. It's 1 times dx dx. But dx dx, that just cancels. And that's why we just leave it as a 1. But dy dx, on the other hand, dy dx does not cancel. And that's actually the thing that we're looking for most of the times. We're always looking for dy dx because you're looking for the slope of the tangent line, which is technically the derivative, which is technically dy dx. And this, of course, is all being multiplied by the first function, which is x. And that's it. That's how you take the derivative. That's how you take the derivative of something explicit, right? I'm sorry, implicitly, right? You apply the rules just like you did before, but now, basically, if you want the shorthand of this, if you're taking the derivative of something where the variable does not match with what you're taking the derivative with respect to, just make sure you tack on the d whatever of whatever you're taking the derivative with respect to. All right, so since my variable here is y, I'm taking it with respect to x, the derivative of y squared is still 2y. That's easy. Just don't forget to tack on the dy dx for the chain rule of the inside function. So if you're not catching anything else, right, if I was asking you to take the derivative of, for example, of 4y to the third, and I was asking you to take the derivative of this with respect to x, then this should be equal to 12y squared times dy dx. That's all I'm asking, is that when you take these derivatives, you now need to start paying attention to what you're taking the derivative with respect to. And if it doesn't match up with the variable you have, you got to tack on the dy dx onto it, right? So if I was taking the derivative with respect to x of, let's say, 4 r cubed, right? It'd be the same thing. This would be 12, but now it'd be 12r squared, but you have to tack on the dr dx, right? So we're paying attention now to what we're doing with respect to. And that's only because now if the functions are implicit, we have to be a little bit careful. Now you'll say, knock me, why didn't we do this before with explicit functions? And we did. We did. I kind of just gave it to you, though. You ready for this? If I had y was equal to 4x squared, and I asked you to take the derivative of this entire equation with respect to x, right? Did you notice that when I wrote my answer, sometimes I'd write it as dy dx? That's because the derivative of y with respect to x comes out to that, right? So do we get dy dx is equal to 8x? And we'd say, hey, that was it. That was our answer. But I'm hoping that you're starting to see that dy dx, that's the idea. It's the function that you're looking at with respect to whatever variable that you care for, right? Usually in this case is x's, right? So that would be why, and that's where this is coming from, right? That's where the dy dx is coming from. And of course, if you wanted to shortcut it, dy dx, if you don't want to write that whole thing down, you could just write that as y prime. That's the shortcut for dy dx. How you guys doing? You okay? You all right? It's a little strange, I know, but hopefully it's not too bad. It's the same stuff that you've been doing, right? But you got to just tack on now that dy dx when you start doing things that have, because it's no longer y equals to, is now this crazy stuff up here where y is included into the equation, and you got to take the derivative of it, right? You got to take the derivative of it. So I'm going to do one example problem, but before I do that, I want to give you the steps here for solving these problems. By the way, you're like, what? We weren't solving the problems yet? No, not yet. We're just learning the technique, right? And then we're going to actually solve a problem. So I'm going to go ahead and write down a problem right here that we want to try to solve. So let's say I have here, for example, x squared plus y squared is equal to 25, right? And I'm asked to find dy dx. I'm asked to find the derivative of x squared plus y squared equals to 25. Okay, so let's go ahead and take a look at this one. Check this out. So to find dy dx, I need to take the derivative of this entire equation with respect to x, right? How do I know it's with respect to x? Because of this. You always look for the bottom part and just see what am I taking the derivative with respect to. In this case, it's with respect to x. So that's how I know I'm supposed to take the derivative of this with respect to x. So let's go ahead and apply what we just learned to this problem. Right? So the derivative of x squared is going to give me 2x, right? But it's technically 2x times the derivative of the inside, which is dx dx. Now, for future preferences, you don't actually have to show me this part. I'm just showing it to you just to show you, like, this is where the idea comes from. Plus, the derivative of y squared is going to be 2y dy dx. And the derivative of 25, I'm hoping you guys can see, the derivative of 25 is just 0. The derivative of 25 is just 0. Okay? So the dx over dx cancels out with each other, and you're left with 2x plus 2y times dy dx is equal to 0. Now remember what I'm asked to find. What am I asked to find? I'm asked to find dy dx. And you'll say, knock me, it's right there. And yes, it is right there. So all you got to do to find it is get it by itself. And now this just becomes an algebra problem. I need to isolate this dy dx to get it by itself to be solved for dy dx. So how do I solve for this? Well, lucky for me, right? We know some algebra. We're going to subtract the 2x to the other side. And I get here 2y dy dx is equal to negative 2x. And then I'm going to divide both sides, right? I'm going to divide both sides by 2y. I'm going to divide both sides by 2y. Why do I do that? Well, the 2y's over here cancel. I'm left with just dy dx. And over here on the other side, I have negative. The 2's cancel out. Negative x over y. And that's my answer. This right here is the derivative of this equation. And that's how you take derivatives implicitly. And that's how you take derivatives implicitly. So I'm going to zoom that out a little bit so you guys can see that. And I want to give you the steps that I did to approach this problem. Okay? I want to give you the steps I did to approach this problem. So let me give you that real quick. And if you don't want to write this all down, you don't have to. You could open up my notes later and just take a screenshot of this. But wow, that's loud. But this is the steps that I would say would help. Wow, that's so small. What is that, for ants? So here are the guidelines. Here are the steps for it. Can you see that okay? Let's make it so I can fit this into here. So here's the steps I did. All right. Differentiate your equation with respect to x on both sides. Right? So that's what I did right here. I took the derivative of the equation on both sides, and I got this guy right here. Collect all terms that have dy dx on the left side of the equation and move all other terms to the other side of the equation. So you end up here with 2y dy dx equals to negative 2x. If you have multiple dy dx's on there, you factor it out from the left side of the equation. I didn't have to because it was already there by itself right here, no other terms. And then divide both sides by what is in front or what is left over from the dy dx. So I divided out by that 2y, so that it doesn't, so that those factors do not contain the dy dx, and factor it out and divide it to the other side. And that's how you get your derivative of dy dx. Anyways, guys, that's it for the time for today. It is 10:37. I appreciate that you're listening through this right here. I'll post up some more stuff for practice. And if you don't get the implicit stuff, don't worry. We're going to go over it some more next time, all right? Other than that, guys, that's it for me. Have a good rest of your day and have a good weekend. I won't see you guys until Tuesday next week. Remember, Monday is not all periods. Monday is even periods next week. So just keep that in mind, guys. Have a good rest of your day. Have a good weekend. Stay out of trouble. Stay out of jail. And don't get pregnant, guys. See you guys later. Have a great weekend. So long.